Today our lesson is going to be on simplifying radical expressions. First we're going to take a look at the properties of square roots and what a radical expression is. A radical expression is anything with either a square root or any kind of root. We call these the nth root. There could be a term right there. When there's no term there, it is indicated that it is a square root. But you could have a 3 here, and we call that a cubed root. Any other numbers, we usually go 4th root, 5th root, and so forth. And this is what's called a radical sign. Now these can also be written as powers. So if I have a radical, a square root of n, it can also be written as n to the 1/2 power. This one can be written as n to the 1 over x power. And if I have something like n to the 2nd power, what's the cubed root of n to the 2nd power? It can be written as n to the 2/3 power. Okay, now let's talk about the properties of square roots. A radical expression contains a radical, such as a square root. Now remember that the expression under a radical sign is called the radicand, this part in here. A radicand is in simplest form if the following 3 conditions are true. If no radicands have perfect square factors other than 1, and no radicands contain fractions. No radicals appear in the denominator of a fraction, and this is one that you really want to keep your eye on, that we cannot have any radical signs in the denominator of a fraction. And the following properties can be used to simplify the square roots. Let's take a look at those. For any non-negative real numbers a and b, the square root of ab is equal to the square root of a times the square root of b. In other words, you can break them apart. So if we had, for instance, the square root of 4 times 9 is the same thing as the square root of 36, or 6. Or we can look at it as breaking it apart as the square root of 4 times the square root of 9, which the square root of 4 is 2, the square root of 9 is 3, 2 times 3 is 6. So either way works. Now not always will you have something that is a perfect square under the radical sign, so that we have to actually simplify it down. All right, so let's take a look at simplifying some square roots. Let's say that we want to simplify the square root of 80. Well, the square root of 80 is not a perfect square, so it doesn't break down nicely. So you want to think to yourself, okay, what is a perfect square that will go into 80? Anything go into 80? Well, okay, the square root of 8 times the square root of 10, but neither one of those are perfect squares. Can you break down the 8? Okay, you could. To where I have the square root of 4 times the square root of 2 times the square root of 10. And what is the square root of 4? 2. Okay, so now I have 2 times, and then I could go ahead and put this back together as the square root of 20. But can I still simplify that down? I sure could. I could break this down as the square root of 4 times the square root of 5. And what is the square root of 4? 2. So don't forget you have a 2 up here. 2 times 2 is 4 times the square root of 5. Now the way they explained it here is they broke it down into several pairs of 2's. In other words, they were thinking of the 4's. 2 times 2 is 4 and 2 times 2 is 4. You could have taken then 16, it looks like, times 5, and that would have been probably the quickest way to have simplified it. And then the square root of 16 is 4. So you really are trying to look for the largest perfect square that will be a factor of 80. All right, let's try a couple. Simplify the square root of 54. Then we're trying to think of the largest perfect square that will go into 54. What are you thinking? Okay, the square root of 9 times the square root of 6. Does that work? Okay, and what is the square root of 9? 3 times the square root of 6. Now, can I break 6 down anymore? No, that's as low as it'll go. Good job. Okay, I want you to try the next one. When you get finished, I want you to raise your hand. I'll check you, and then you can check your partner. All right, what's a perfect square that goes into 180? Did you find one? Okay, some of you did. 36. The square root of 36 times the square root of 5. Now, did you have to start with 36? No, you could have started with 9 and 20. That would also have worked. 36, what's the square root of 36? 6 times the square root of 5, and that's as low as we will go. Okay, let's take a look at how do we multiply square roots. Just as in the former example, we broke them apart, we can also put them together. If I have the square root of 2 times the square root of 14, and I notice that neither one of those can be broken down possibly, well then let's put them together. We can say that the square root of 2 times the square root of 14 is the square root of 28, and then I know that what is a perfect square that will go into 28. Okay, the square root of 4 times the square root of 7 gives you 28. Therefore, we have 2 times the square root of 7. All right, let's try a couple. The square root of 5 times the square root of 10. Okay, I like to put them together first because I'm thinking the square root of 50. Okay, now let's break that down. What is a perfect square that goes into 50? Is there one? Yes, there is. The square root of 25 times the square root of 2. Sometimes it takes you a while before you can come up with them. And what is the square root of 25? 5 times the square root of 2. And that's as low as we go. Okay, in this case, let's try doing it the way they gave this example here. This can be broken in as the square root of 2 times the square root of 3 times the square root of 2 times the square root of 4. That would work. Okay, I know that the square root of 4 is a 2. And if I take the square root of 2 times the square root of 2, that's actually the square root of 4, which is 2. So now I have 2 times the square root of 3, or to put it in simplest terms, 4 times the square root of 3. Now oftentimes I think it's just easier if you go ahead and put them together first. The square root of 48 and then breaking it down. Okay, in this case, I could have broken it down as the square root of 16 times the square root of 3, which is 4 times the square root of 3. So I think it's easier if you can find or in your mind think of perfect squares. Okay, next let's simplify a square root with variables. We start out with the square root of 90, x to the third, y to the fourth, z to the fifth. I like to break down the 90 first. What is a perfect square that goes into 90? Okay, I can think it as the square root of 9 times the square root of 10 times x to the square root of x to the third times the square root of y to the fourth times the square root of z to the fifth. Okay, we can break down the 9. The square root of 9 is 3. Okay, can I take 10 out? Is there anything that I can do to simplify that one? Nope. Okay, so he's going to stay under. So this is 3. Now, how do I get x's out? When I look at variables, remember I kind of want to think that when I'm looking at a square root, I'm talking about pairs. I need to have 2 of a variable. In other words, something to the second power. So if I take an x to the second power out, the square root of x to the second power is x, and then I still have, under the radical sign, an x. Y to the fourth power, I can actually get 2 of those out. So I leave it as y to the second power, and I can get 2z, z to the second power, with 1 still left under the radical sign. So my final answer will be 3 times x, y to the second, z to the second, times 10xz, the square root of all of that, 10xz. Now, why do I have an x in absolute value, do you think, here? Because since I'm not taking it to a power, it actually has to be a positive number. It cannot be a negative, and that's why we include it in the absolute value symbols. All right, now let's try some. Simplify the square root of 32r squared, k to the fourth, t to the fifth. Okay, we can break it down. the square root of 16 times the square root of 2, square root of r to the second, square root of k to the fourth, times the square root of t to the fifth. Okay, this we can simplify to a 4. What else can we get out? We get out the r, 2 k's, 2 sets of t's, and then what do I have left under the radical sign? 2 times t, the square root of 2t. Now, does anything need to be in the absolute value symbols? Yes, the r does. All right, good job. Now let's try the last one. The square root of 56, xy to the 10th, z to the 5th. Okay, I have the square root of 4 times the square root of 14, square root of x, square root of y to the 10th, square root of z to the 5th. Okay, this will be a 2. Anything else come out? How many y's will come out? Okay, to the 5th power is what we have left. Good. And what about the z's? Z to the 2nd, but don't forget that there is 1 left over. So what's left under the radical sign? Okay, 14, x, and z. Okay, do any of these need to have an absolute value symbol around them? Yes, this one does, because it's an odd power, and that indicates that we have to have it as a positive. Next, we're going to work on the division property of square roots. To divide square roots and simplify radical expressions, you can use the property as shown here. If I have the square root of a over b, that's the same thing as saying the square root of a divided by or over the square root of b. Okay, so let's take a look at this one. Which expression is equivalent to the square root of 35 over 15? We could probably break that apart, the square root of 35 over the square root of 15, and see if we can simplify that. Anything go into 35? Okay, in this case, you notice that there's nothing that goes into them that are perfect squares, so we have to do a process that's called rationalizing the denominator, because one of the rules at the very beginning we talked about, we can never have a radical in the denominator. So we're going to do a process called rationalizing the denominator, in which you multiply both the numerator and denominator by the divisor, the denominator, which is the square root of 15 in this case. It's kind of like finding the common denominator when you're working with fractions. So here I'm going to end up with the square root of 35 times the square root of 15 all over, when I have the square root of 15 times the square root of 15, I get 15. Because it would have ended up being the square root of 225, which is 15. So it's kind of what I consider it sets it free. All right, now let's take a look and see what's happening at the top. Okay, if we find the product of 35 and 15, we get, I believe, 525. So we have the square root of 525 over 15. Now, can I break this down into a perfect square? 25 will go into it. 25 times what? 21. Okay, and what can I do with the 25? The square root of 25 is 5. Therefore, we have 5 times the square root of 21 all over 15, and that's our final answer. All right, let's try one. Let's simplify the square root of 6y over the square root of 12. Okay, looks like we're going to have to rationalize our denominator. And let's see if we can simplify this first. Okay, looks like we can. We can do the square root of 4 times the square root of 3. So that I end up on in the bottom, or the denominator, 2 times the square root of 3. And at the top, square root of 6y. Okay, now what do I need to get rid of? Okay, I need to get rid of the square root of 3, so that's why I'm going to rationalize. It's called rationalizing the denominator. Multiply both the numerator and denominator by the square root of 3. So now I have the square root of 18y all over 2 times 3, which is 6. Okay, can I simplify what's at the top now in the numerator? Yes, the square root of 9 times the square root of 2 times the square root of y, all over 6. And we can simplify that as 3 times the square root of 2y, all over 6. Am I done? No, it looks like we can simplify 3 into 6 to get final answer of the square root of 2y, because this becomes a 1, all over 2. Is that your final answer? I believe it is. Now we can also use something else, and this, let's take a look at this example. We have 3 over 5 plus the square root of 2. How do we get rid of this when you have 5 plus the square root of 2? And we're going to use something called a conjugate. Binomials in this form, a times the square root of b plus c times the square root of d, and a times the square root of b minus c times the square root of d, where those are all rational numbers, are called conjugates. Okay, and if you were to do FOIL on those, you can find that it's the difference of 2 perfect squares. Okay, and we can prove that down here in this example. We'll do that. We'll see what we get. Okay, so we're going to use conjugates to rationalize this denominator. If we have 3 over 5 plus the square root of 2, we're going to need to multiply both the numerator and denominator by 5 minus the square root of 2. Okay, so when I distribute this with the 3, what happens? I get 15 minus 3 times the square root of 2. Okay, and then on the bottom, let's work that one out. Okay, now let's off to the side. Let's show what happens here. We haven't worked enough with FOIL to get this down, maybe where you know the shortcut. So we're going to prove to you what happens here. We get 25. That's the first, the outer, minus 5 times the square root of 2, inner, plus 5 times the square root of 2, and then I have minus the square root of 4. So we end up, those cancel out, and we end up with 25 minus, and the square root of 4 is 2. What is 25 minus 2? It is 23. Okay, I don't think there's anything else that we can pull out or simplify here, so this is your final answer. We have just simplified by using a conjugate. All right, now let's try a couple. We recognize that we have a radical in the denominator, which we can't have, but we're not multiplying those two, so we must then go ahead and do the process called rationalizing the denominator and multiply both of them by its conjugate, 2 minus the square root of 2. And when I distribute, I get 6 minus 3 times the square root of 2. Okay, and what do we get on the bottom? Okay, and if you still need to work it out, that is fine. 2 plus the square root of 2. You FOIL it, 2 minus the square root of 2. I get 4 minus 2 times the square root of 2 plus 2 times the square root of 2 minus the square root of 4. Okay, just know that those two cancel out and that you always just multiply your last two terms and you'll get the hang of it. Okay, so I have 4 minus 2, which is 2. Okay, so my final answer is 6 minus 3 times the square root of 2 all over 2. All right, you try this last one here. When you think you have the right answer, raise your hand and I'll come check you. All right, you have to take both of them times 3. Now, because this is a minus, it will be plus the square root of 7. And when I distribute, I get 21 plus 7 times the square root of 7 all over, and what will this be? Have you gotten the shortcut down yet? 9 minus 7. That's right. which is 2. And that's your final answer. So today we worked on simplifying radical expressions, and we've learned the properties that have to do with those. Let's review that. Remember that no radicand can have perfect square factors other than 1, and that no radicands contain fractions, and that no radicals appear in the denominator of a fraction. Okay, those are the basic rules that we've gone over today in simplifying radical expressions.